Alright, let's talk about Newman projections. So, what's the idea of a Newman projection? Well, if you'll take a look at this over here, this is a 2D picture of a molecule, and what this allows me to do is if I hit this, I get a three-dimensional model. So, the reason I've put these different groups on here is that you could tell how this molecule is oriented in space. So say I wanted to look down this bond here. We'll call this the C2-C3 bond. So first I need to look for that iodine and that chlorine, and then I need to rotate and turn the molecule until it looks something like this. Notice that when we turn the molecule and orient it so that we're looking down this bond over here, we can see 6 groups around this carbon. We can see in the front carbon the iodine, the chlorine, and the CH3 of this, and then in the back we're sort of blocking out this backward carbon, but we can see what it's attached to. We can see the bromine, we can see the methyl group, and we can see the fluorine. Similarly, if I turn it around and I look down the other way, if I look from this side, I'll see in the front carbon it has that Br, that F, and that methyl group. In that back carbon over here, I can see its groups. I can see the Cl, I can see the iodine, and I can see the other methyl group. This is what we refer to as a Newman projection. So, again, say we had this molecule and we wanted to look down this sigma bond. What we saw in 3D space was this. When we make a simple two-dimensional diagram of what we see, that's what we call a Newman projection. Notice that a Newman projection is looking at that front carbon. It has its groups, the Cl, the methyl, and the iodine, and then the carbon that's being blocked, we can see its groups as well, the fluorine, the methyl, and the Br. The Newman projection is just a simplified way of viewing the molecule like this. And again, the point of the Newman projection is to look at a molecule down a sigma bond and to see the two different sets of groups that are oriented along that sigma bond. Okay. The other thing you should notice is that the wedges appear on the same side and the dashes appear on the same side. So let's turn the molecule so it's a little bit easier to see that going on here. So from our picture up top, you'll see that the chlorine and the bromine are dashed, and over here in this side we'll see that both of them are dashed, and over here we'll see the wedges, the fluorine and the iodine. Because remember what these wedges and these dashes mean as far as three-dimensional space. So a wedge will come out at us, so out of the screen towards wherever you're sitting, and the dash will go in the opposite direction. The dash will go into the paper or past your computer. So if you're looking at the molecule as if you're looking down the sigma bond, and I suggest playing with that three-dimensional program I was just using, but you'll see that if you're looking at it down this way, everything that is coming toward you out of the computer will be on the right, and everything that is going into the computer will be on the left. Now if you're looking the other way, if you're looking this way through the, I guess, right to left, you would see the opposite, right? So like if you were looking at it this way, you'd see the iodine and the fluorine on the left, and the chlorine and the bromine on the right. So again, when you're doing this, just think about which way you're looking. If you're looking left to right or right to left, and then remember what those wedges and dashes mean as far as where things are going to be in three-dimensional space, either toward you, the viewer, or away from you, the viewer. Okay, so why do we care about these Newman projections? Well, you'll remember that molecules are allowed to rotate about their sigma bonds. There's nothing that keeps those molecules in place. So all these groups that you see here, they could spin around in various conformations. Some of them are more energetically stable than others. what you'll see most often is this sort of diagram here. What's going on here is that you have the rotation of the molecule versus the energy of what's going on. So they'll also show you the Newman projections corresponding to these energy states. The worst kind of, confirmation you could have is when these front groups have spun around so that they're right in front of the back groups. And that means they're basically interacting in space. Those electron clouds in each of those groups are getting close to each other, and that's unfavorable energetically. What we call that is sterics. Steric strain, sometimes people call that angle strain, torsional strain, all those different kinds of strains. But they all fall under the umbrella of sterics. You'll see that the high points in the energy come whenever you have something called eclipsing. Eclipsing is what I just mentioned before. It's when the groups of the front carbon in that sigma bond are directly in front of the back groups. The most stable conformations you'll see at these valleys here are when you have something we called staggering. So again, here we call this eclipsed, and at the low points we call this staggered. And staggered is exactly how it sounds. It means the groups are spaced out, just like you see here, where you can see all 6 of them. There aren't any groups that are blocking each other. So that's what we refer to when we call it staggered. So you also see that some of these eclipsed conformations are higher in energy than each other, and some of these staggered conformations are lower in energy than some of the other ones. Well, there's small differences. So again, eclipsed is what we'll refer to as unstable transitional states in your molecule, and in staggered, the best conformation you could have is something called anti. Anti means the largest groups are opposite each other on the Newman projection. So if there's 4 hydrogens and 2 methyl groups, the anti-staggered conformation is the one where you have these methyl groups oriented opposite. Over here you'll see that these methyl groups aren't opposite the ring, they're actually adjacent to each other. We call this a gauche interaction. Gauche interactions are unfavorable. It means your electron clouds are too close to each other. So if we go back to this over here, you'll see that if you look down this bond, the this methyl group and this iodine are gauche. It means they're sort of getting closer together in space, and that's sterically not so great. So if you have big bulky substituents, branched alkyl substituents, these hydrogens start getting very close to each other, and that's not very favorable. So that's what we mean when we refer to gauche interactions. Okay, so notice that because there's a gauche interaction here, this staggered conformation is higher in energy or less stable than this anti-staggered conformation. So again, how do you point out gauche interactions? Well, again, you can either look at how they're oriented in space. If we look down this bond, you see that these methyl groups are getting close to each other, or in the Newman projection, you'll see that the groups are adjacent to each other, just like this. Okay, that's pretty much all you need as far as theory goes. Let's try doing some problems. So, this is an example of an exam question, and we have what is called a sawhorse projection. The reason it's called a sawhorse projection is because the molecule looks like a sawhorse. And we want to convert this to a Newman projection and then draw 3 different staggered conformations and identify which staggered conformation is the most stable. Okay, so the first thing I would suggest doing is you have that sawhorse conformation, and what you want to do is you want to turn the back around so that you have one of these, I guess, I don't know how to call them, but groups of 3 oriented upward and one of them oriented downward. So see here I rotated this 120 degrees and then 60 more degrees, and I got this. So the Cl is now facing downwards, and these H's are now facing this way. Once you've done that, you could imagine reorienting the molecule so that you're looking directly down this sigma bond. What that'll get you is a Newman projection that looks like this. Okay, so how do you go from one staggered conformation to another? Well, that's not too bad. You simply do a bond rotation, and each of these groups will move over 120 degrees. So if you do that once, what you'll see is this. And if you do that twice, once again, you take this structure and you move everything 120 degrees, you'll see this. And typically you fix one of these groups, so I usually fix the front, so these three in black won't move, but these colored ones will move. And these are your three different staggered conformations. At this point we want to tell which staggered conformation is the best energetically. So here, notice that you have a fluorine-chlorine gauche interaction. So that you'll see is right here. Whenever things are adjacent to each other on the Newman projection, that's a gauche interaction. You don't consider gauche interactions to hydrogen because hydrogen is so small, it's not going to have any steric or spatial interference with anyone else. Over here you'll see that the methyl and the chlorine are pretty close together. So they're adjacent. This is one gauche interaction. This is another gauche interaction. Last over here we have this, and that's it. So now we've listed all the gauche interactions that we have. Okay, so what makes particularly bad gauche interactions? And it's the same kind of things we're looking at when we're talking about chairs. So bulky alkyl groups give high energy gauche interactions. So the worst thing you could have is an alkyl group next to another alkyl group. Halides next to each other aren't so bad. Alkyl and halide is somewhere in between that. So if we're looking at these three conformations, what we'll see is that the least stable one, it makes sense that it would be this, because it has both the alkyl halide gauche interaction and it has the most gauche interactions. When we're looking at the other two, we're comparing a ClF, a halide-halide gauche interaction, versus a alkyl halide gauche interaction. Remember, bulky alkyl groups interacting with other things is bad, so this is not so great, and this is better, because halide-halide is not as bad as alkyl halide or alkyl alkyl. Let's try another problem. Again, it'll be with the sawhorse projection. Alright, so here once again we have a sawhorse projection, and we want to get the three staggered conformations if we're calling this carbon 2 and this carbon, well, this carbon 2 and this carbon 3. It's consistent with the naming because this is the 2 position, so this is 1, 2, 3, 4. I suggest pausing the video and giving this question a try. Okay, so the first thing to do is, again, you have that sawhorse projection. You want to rotate the group in the back so that it looks like this. So again, you have those two Y's, the downward facing Y. Well, okay, I think you know what I mean. They could intersect and you'll get your Newman projection. The first one will look like this. And again, you don't move the carbon in the front, and you rotate the carbon in the back 120 degrees, and you'll get these two Newman projections. Now we look at each of the carbons, well, each of the Newman projections, and we list their Gauche interactions. So here we have a CH3CH3, a CH3F, and an F-ethyl. You should already be seeing that the ethyl group will be the worst energetically, so we want to minimize gauche interactions with the ethyl group because it's the biggest alkyl group we have. Our second structure, we have a CH3, a CH3, a CH3 ethyl, and an F ethyl. And lastly, we have CH3 ethyl and a CH3F. Now don't automatically assume that because this has the lowest number of gauche interactions that this is the most stable. Again, we need to look at the substituents that are involved in each gauche interaction. So again, alkyl, alkyl, it's high in energy, alkyl, halide is lower, and halide, halide is lowest. So over here, what we have to pay attention to is these two are the worst kind of gauche interaction you could have. You have a large alkyl group and a small alkyl group. That's bulk on bulk. That's going to be unfavorable. At this point, you could already conclude that because this Newman projection doesn't have that unfavorable methyl-ethyl gauche interaction, that it's going to be the most stable. In fact, it is what we call anti. So the largest group, CH3, on one of the carbons is opposite the largest group on the other one. So the ethyl and the methyl are anti to each other. Over here, now we could compare these two directly. We could see that this has another unfavorable alkyl-alkyl gauche interaction. So this will be the least stable, and this will be somewhere in between. Okay, let's try yet another problem. Okay. So we want the 3 staggered conformations of this molecule. I suggest you try it yourself. Okay, I'm going to assume you tried it, so I would start with this. At this point, I would also add in those hydrogens, because that's important. And then what makes it easy to see the relationships you're going to get is if you just tilt your structure so that it looks like this. And then you should remember from what we looked at before that if I'm going to look at from the C2 to C3, I'm going to see these wedges appear on the right hand side and these dashes appear on the left hand side. What that would get me is a Newman projection that looks like this. So again, the carbon in the front, we see this methyl going directly down. We see the wedge on the right, the dash on the left, and over back here we see this methyl going upward, and we see again this wedge on the right, this dash on the left. Once again, once you've generated that Newman projection, it's not too difficult to get the other two. So you just fix this in the front, don't do anything with these, and you rotate these. So did I? Oh, I actually rotated the ones in the front. So again, you could do either. So these back ones I kept fixed this time. So the H, the Br, and the CH3 would be the same. The front I rotated. So the bromine moved from here to here. The hydrogen moved from here to here. And similarly, going from this one to this one, the bromine moved yet again. The hydrogen moved here. The methyl moved around. In this question, they didn't ask us which one was most stable. Well, actually, it does ask us which one's most stable. Okay. That's not too bad. So again, you look at these, you label what we have. Here we actually have anti for the methyl groups, anti for the bromines. So I can already tell this will probably be the most stable. Over here we have tons of gauche interactions. We have CH3, CH3, we have CH3, Br, we have Br, Br. And over here we have essentially the same. So CH3, 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 Br, Br, Br. So it'll end up being the same, but I would say the most stable is probably this one on the left. Alright, let's try yet another problem. And the structure is this. So pause the video, give this a try. Okay, so again, I would just rotate the structure so that it looks like this. Look at it along the C2 to C3, and you'll see that this methyl group is facing up, this wedge will be on the right, this dash will be on the left, and in the back, this methyl group will be facing down, the wedge will again be on the right, and the dash will be on the left, because the wedges and dashes need to appear on the same side of the Newman projection. Once you've done your bond rotation, looks like this time I again rotated in the front, so that went there, and so on and so forth, and then from here to the next one, I again rotated the front. At this point in time, list the interactions that you have occurring in each Newman projection. So CH3OH over here, and SH CH3 over here. This one we have methyl-methyl, we have methyl-CH, and we have CH-OH. And over here we have CH3, and yeah, essentially the same things as over here. I think the only difference is this, and you'll know that sulfur is a larger atom than oxygen. It's in the same family, it's in the row below, so this will lead to more steric strain than oxygen. And this not only has the lowest number of gauche interactions, it doesn't have that alkyl-alkyl or the methyl-methyl gauche interaction. Okay, so you'll see that Newman projections really aren't that bad. They'll probably be the safest points you get on your first exam. The only real way to make them tricky is when you start introducing chirality, but we'll talk about that some other time.